1, 2, 3. 1, 2, 3. OK. All right, we start. Okay, good morning. Okay, so today is already the fourth lecture. We'll talk about quantifying uncertainty. So this is the part where usually students are getting less comfortable with the materials of the course. I will take the time to explain slowly all these things, and supposedly today in this lecture you will see things that you have already learned before in probability theory or in statistics. You should be familiar with everything, hopefully, but I will, even though, take the time to re-explain, because we will base basically everything that we'll see. I mean, all the following lectures from now on will be based on probability theory. We'll only consider probabilistic models. And so it's very important that we speak the same language and that we agree on the definitions. Okay, before that, I just wanted to make a comment. So I don't know if some of you have seen, but on Tuesday, I mean, this week was the week of the Nobel Prizes. And so a few of them have already announced the prize in medicine, physics, chemistry, and today will be about literature. And I don't know if you've seen the news, at least on Tuesday. So on Tuesday, there was deserved the Nobel Prize of Physics. And the Nobel Prize of Physics was given to these two guys, John Hopfield and Geoffrey Hinton. For what? For foundational discoveries and inventions that enable machine learning with artificial neural networks. So the Nobel Prize of Physics was given for AI. Okay? And Geoffrey Hinton is someone I've already talked to you about. Is this guy that, if you remember, so during the introduction, we listened to Yann Lequin, but we also listened to, where was it? To this guy, who is Geoffrey Hinton, okay? Who now got the Nobel Prize of Physics. So you may wonder, but why do we give the Nobel Prize of Physics for discoveries in computer science, in AI? So these two guys, they've worked during the 70s and the 80s on neural networks that were model of associative memories. So they wanted to understand how human brains, biological brains, are able to maintain basically memories. How do we do that? Where do we store this information? And so they proposed a model for that. The first one is known now as the Hopfield network, which is like one of the first kind of neural network of the same kind that we'll see later on in the course. And then Geoffrey Hinton, after that, improved this version, this neural network, and worked on what is now known as Boltzmann machines, which are generative models, so neural network that you can use to generate data. Okay? So this was nice, and so I think it's a very important recognition for the field of AI that what we do in this field is important. So, but why does it relate to physics? Actually, the very first formulation of this network is based on similar models that have been proposed to study other physical processes, like ferromagnetism with the Ising model, which was proposed in the 20s, or spin glass models, which are used to model matter. And so the same model could be reused to also study biophysical processes like associative memories in biological brains. And after that, actually, these models have been also reused to study, once again, physical processes, more classical physical processes, like disorder systems that you may have in condensed matter physics. Like how can you describe and model matter? This is something that you can also do with these neural networks. Obviously, the discovery is not about just these two very specific neural networks. It's also about what they triggered. So they triggered this whole field of AI and of deep learning and of all the improvements that we've been talking about already for the past lectures. Okay, so this is a very nice announcement in my opinion, so I was very happy to hear that on Tuesday. But then on Wednesday, so yesterday, was announced the Nobel Prize of Chemistry, and the Nobel Prize of Chemistry has been awarded to David Baker, Demis Hassabis, and John Jumper. And Demis Hassabis and John Jumper are the inventors of AlphaFold. AlphaFold is a neural network which is used to basically predict the 3D structure of proteins. And this is something I've already told you about during the introduction. I told you that, okay, we can do all these things, but we can also solve problems that no one could solve before. And AlphaFold was one of those. And I think I even mentioned that eventually, they would get the Nobel Prize for this discovery. So now they have it. So it's really important. So this is just to say that everything that we are doing in AI is interesting for itself, but it's also, and in my opinion, even more interesting because it has applications now in many scientific fields and also in many technological fields, of course, but really, now it's seen really as a very important tool to move science forward. Okay, so if you're interested by that, please feel free to watch again this video or to watch it once if you've not done that yet. All right. Okay. Okay, so where are we currently in the course? So we talked during the first lecture about agents, and we've described a few high-level architectures or principles that we could try to implement inside these agents to have some kind of intelligent behaviors. We have talked about goal-based agents or utility-based agents, and we've already seen a few implementations of these agents with agents that act by solving a search problem. This was the topic of the second lecture, where we've talked about algorithms like A*. And then we considered extensions for environments in which we have multiple agents acting together or adversarially in the environment. And last week, we talked about adversarial search and algorithms like Minimax. Okay? So in what we have considered so far, we have assumed that we have usually a perfect knowledge of the environment and also of the other agents. Okay? We have seen one exception to that already last week when we considered stochastic environments, which was the case where we could not predict what was the resulting state to which we would arrive when we start in some state S, take some action A. In the previous cases, we were assuming that we had a deterministic transition from S to S prime. Okay, but in the stochastic environment, we don't know, okay, and we have to take this uncertainty into account. Okay, we don't know what will be the resulting state. Okay, so today we'll formalize this framework of having to deal with uncertainties, and we'll then be able to use this framework not only to act in stochastic environments, but also to act in environments for which information is only partially observable. Okay? So in cases where you don't know the state, you only get a noisy and incomplete and partial observation of the states. How do you use this information to estimate the state and then to act optimally in the environment? Okay? So that will be the motivation of why we are talking about all these concepts, why we are talking about probability theory, and so on. All right, so the menu for today will be quite simple. We'll do basically a recap of probability theory. We'll talk about random variables. We'll talk about probability distributions. We'll talk about inference problems. We'll talk about assumptions that we can make on the model that we consider to simplify the inference procedures. And finally, we'll talk about the Bayes rule. Okay? So as I said there at the bottom of the slide, do not overlook this lecture. It looks easy. It's not complicated, but it's really important that you understand this concept very well. All right, so quantifying uncertainty. So first of all, how would you yourself describe uncertainty? What does that mean to you? Yes?
It's a situation in which we are not sure about some things, and so there is some part we don't know.
Okay, so it's about what you don't know. Exact. And why couldn't you know some of these things? What could be the reason that there are things you know you don't know?
Because we can see the world environment, for example.
Yeah, okay. So a way to rephrase that is that the environment is maybe too complicated, and the observations that we get out of this environment are just imperfect, for example, measurements in case of sensors, or it just, even ourselves with our eyes, we just see 2D images in a sense, which we interpret as 3D with our brain, but this is something we do internally, we just get 2D images. And from this, we infer the 3D world. Yes? Okay, so the environment could be actually stochastic. Okay, so even if you knew perfectly the state of the environment, you could not predict the next state because the transition is itself stochastic. Yes? Okay, we'll formalize that in a few slides, but just to motivate once again, let's consider a toy example related to the world of Pac-Man. So let's assume that we have a grid world like this, and somewhere there is a ghost. Okay, but since it's a ghost, we don't see it. Right? However, we are equipped with a sensor which we can trigger at any of those cells, and we'll receive as an output of the sensor an indication of the distance of the cell to the ghost. Okay? And we'll get a red color if the ghost is at this position. We'll get an orange color, so we get only 4 values. We get to see either red, orange, yellow, or green. We will get a value which is orange if the ghost is 1 or 2 cells away from the current cell. We would get a yellow indication if it's 3 cells away, and we would get a green indication if it's 4 cells away or more. Okay? However, the sensors are noisy. Sometimes they misbehave, okay? And so you would get a color which should not have been the color that it was supposed to be because there are issues, problems, if you want, stochastic outcomes with the sensor themselves, okay? So the sensors are noisy. It could be that, for example, you see a red color, which should indicate that the ghost is at this position, but if the sensor misbehaves, if you get a noisy and wrong observation, then that means that the ghost is actually not there. Okay? And what we'll assume is that we know our instrument. Okay? We know how it works, and also we know when it doesn't work. Okay? And we'll incorporate all of this knowledge into a probability distribution, which we'll assume to be known, which will give us the probability of seeing some color given the distance of the cells to the ghost. Okay? And that probability distribution will include this normal behavior, but also the noisy outputs that we may observe. Okay? All right, so let's play a game. Now we have to find the ghost. Okay? And we get only one chance to kill it. Okay? So we are free to sense all the cells if we want, but then we just have one shot if we want to kill it. So if we want to kill it, we must be very certain about the location of the ghost. Okay, so what will happen is that we'll sense some of these cells. For example, the first cell here would correspond to a yellow measurement. green measurement, sorry. Then we get the second one, which is red, orange, and then a lot of green. What could this mean? Would you expect these patterns? So, who thinks the ghost is there at this position? Raise your hand. Why? It's red. So what makes you think otherwise? Yes?
You'd expect orange squares around.
Sorry?
You'd expect orange squares around the red one.
Exactly. So if it was truly there, we would expect that in the immediate neighborhood of that red cell, we would have orange cell. Okay, but we see many green cells. So what does that mean? Are you confident about that?
Well, yes, because it's more likely than, I would assume it's more likely than only one cell has a switch from green, for example, to red, than all the green ones switching from orange to green.
Yeah, so we have two choices. Either the ghost is there, and in this case, this red measurement is an actual correct measurement, but this could be explained only if all these green measurements are actually noisy measurements, which is very unlikely to have so many of them to be green. Okay, it's still not zero probability to happen, but might be very unlikely. Okay, or the other case is the ghost is not there. This red measurement was a noisy measurement. Okay, in this case, all these green cells are quite consistent with also this scenario. Okay, and then we have to ponder between these two choices. Okay, let's continue. Where is the ghost? Where do you think is the ghost? Is it there at the red position? Can you raise your hand if you think it's there? Okay. Why? How do you do that? Yeah.
Because there is only one cell that is not consistent with the others.
Okay. Yeah. So we have this green measurement next to the red one. Okay. But from everything we see around it, mostly orange one, the most likely scenario is that the ghost is actually there and the green one is a noisy measurement. It's a wrong measurement. The question I will ask you next is, how do you do that? How do you reason and determine that the ghost is actually there? Could you describe this reasoning process that you do so accurately that you could actually implement it in a computer program? Okay, and in this case, the ghost was actually at this position. Okay, so the goal of today will be to try to solve this game using the probabilistic framework. Okay, and at the end of the day, at the end of the lecture, we'll have a computer program that actually solves this game very easily. Okay? Do you have an intuition about how you should do that? It seems so natural for everyone. Okay, even though probability theory is not natural for everyone, but you are able to do that very easily. Yes.
We can check the pattern from we take each case and we check the pattern if % of the pattern is right in it.
How do you check all the patterns?
As we know, like orange is too far away, we check like a cross around all the red ones, and if a certain % of the case are in the right color, is it there?
How do you determine these certain persons?
About how the nose is, there is this
Mm-hmm.
effect.
Okay, so we'll see how to make this more precise. But you will see that using simple rule, simple probability theory, I will manage to solve this problem. Okay. So why do we do that? Why do we care about uncertainties? Why do we care about the probabilistic framework? It's because, remember, we have defined AI in this course as simply the fact of maximizing the utility of the agents. And when we defined that, I added a very important word, which is that we want to maximize the expected utility. Okay? And so today, what we'll properly define is what we mean by this word expected. Okay? This expected will be based on the probabilistic assumptions that we make. Okay? Okay, uncertainty. The general setup that we'll consider goes as follows. So we'll assume that we describe a system, an environment with variables. Okay? Like, for example, the position of the ghost would be a variable, or several variables. And we may have uncertainties about these variables because there are maybe some of those that you observe and some others that you do not observe. Okay? So the first case corresponds to the easiest, which correspond to the observed variables, okay? Which I will also call the evidence variables. So these are variables for which you know the value, okay? And so you can assume that the agent knows certain things about the state of the world or the state of the system, okay? Again, for example, in the case of the ghost hidden on the grid cell, on the grid world, the observed variables would be the readings that we get from the sensor. Okay? So, for example, we could have as many variables as we have grid cells, and then for each, we have a reading value. Okay? And that's a random variable. Okay? Because if we repeat the measure at the same self, we could obtain another value. Okay? Then we have unobserved variables. So these are all the things that you assume about the environment, but that you know you don't know. Okay? And these will be the variables that the agents need to reason about. Okay? For example, where is the ghost? What is the most likely position of the ghost? Okay? That's a variable. You can model that as a variable, but you don't observe that variable. All right? Does that make sense so far? Okay. Then we'll assume also that we have a model, and specifically that we have a probabilistic model. And specifically what we'll do is that we'll say that the agent knows or believes something about the observed variables and how they relate to the unobserved variables. Okay? So the kind of drawings I will do very often is that I will assume that I have one or several evidence variables, everything that I observe. Okay? I have also other variables that are hidden to me, right? And I'll make assumptions about how these variables relate to one another. Okay? And these assumptions, in what we'll see, will be defined by a probabilistic model from one to the other. And usually we'll define a probabilistic model from H to, okay? I'll assume a conditional probability distribution that explains, that gives me the probability of each value of the evidence variable given some value of the hidden variables. Okay? I will define that later on more precisely. Okay? And with these three components, the observed variable, the unobserved variables, and a probabilistic model, then probabilistic reasoning will provide us with a framework for managing our knowledge and our beliefs. Okay? Now the question I will ask you is a very simple question. What is a probability value? How do you define a probability?
chance of an event will occur.
It's the chance of an event will occur. Okay. Anyone else? Yes?
It's a number between 0 and 1 linked to the, which represents the realization of an event.
Okay. So it's a number, that's correct. That represents the realization of an event. Yes? Anyone else? Who followed the probability class or statistics class? So you should know. Yes?
It's the number of states that we want to observe divided by all the different states possible.
Yeah, what do you mean?
Like if we want the probability to arrive on one state,
Mm-hmm.
it will be all the way to arrive on the state divided by all the way to all the possible states. So we can do.
Okay. So the only thing I agree with so far is that probability values are numbers. Everything you have said after that are interpretations of these numbers, but they don't define the numbers themselves. Okay? So we'll see that, but it's really important that you dissociate the probability values, the number, from how you interpret them. Okay? So let me explain that. So first, we can consider assertions that we want, for which we want to assert how confident we are or how uncertain we are. Okay, and we can do that with probability values. Okay, and they will express. So a probabilistic assertion will express the agent's or our own inability to reach a definite decision regarding the truth of a proposition. For example, if you say that the probability of the ghost, some variable which is hidden, to be at some position, I don't know, 1, 0 on the grid, okay? If you say, so this is a number, okay? And this is a probabilistic assertion, and you would say, for example, it's 0.6, okay? So this is what we call a probabilistic assertion, and it means that it basically expresses our inability to say confidently and definitely that the ghost is at this position 1, 0. Okay? We are just saying, I believe that there is a 60% chance that the ghost is at this position. All right? And these probability values, this number, they summarize two things. They may summarize our ignorance. Okay? There are things we know we don't know. Okay? And this ignorance can be theoretical or practical, or because we are lazy. Okay? We may well know that the world is very complicated, but we make assumptions. We make an assumption about this probabilistic model, which is a simplification of the real world. Okay? And in this case, everything we know we approximate can be summarized also as probability values. Okay? Okay, and so these probability values, they will relate to propositions to one's own state of knowledge, or more precisely, to your lack of knowledge. Okay? And then the question I ask is, what do they represent? Or I ask what they are. What they represent is a subjective interpretation that you assign to these numbers. And there are two main schools related to the interpretation of probability values. What we call frequentism, or frequentist probability values, and Bayesianism, or Bayesian probability values. Okay? And so in the first interpretation of a probability value, which is the objectivist frequentist view, is that probabilities will correspond to real aspects of the universe or of the world that you are studying. Okay? And they will correspond to the chance of seeing some event, as one of you said. Okay, that's an interpretation. And so these probability values, in this case, you associate to them properties or propensities of the variables that you are studying. okay, like a frequency. Okay? So if you take, for example, just a coin and you throw it in the air, the fact that if you have a fair coin, it will come up head with some probability, let's say 0.5, okay, is a property, it's a propensity of the object. Okay? Now, the framework or the interpretation that we'll adopt for probability values is not this one. What we'll use instead is the subjectivist Bayesian view, which says that probability values, these numbers, they are just a way of characterizing our own beliefs, our own knowledge, or our own lack of knowledge. Okay? And so the probability values themselves, these numbers, in the Bayesian setting, they do not have any external physical significance. They just represent our own subjective knowledge or beliefs. Okay? And this is the interpretation of probability values that we'll use. Okay? And to show you that this is subjective, I mean that this, what we mean or how we interpret a probability value is just an interpretation, I will show you next that you can actually define probability values just mathematically without talking about frequencies of objects, without talking about beliefs or whatever. Okay? You just need to define 3 axioms, and you are done. You have defined probability values. Okay? So it's important that you dissociate the interpretation of these numbers, these probability value numbers, from their actual mathematical definitions. So how do we define a probability value? So we do that classically using the Kolmogorov's axioms of probability. So there are a few definitions. I will need to go through them. So, but we say that we begin with a set, omega, which we call the sample space, a set of points. Okay, let's say this is omega, this potato. And inside, we have sample points or possible realizations. Okay? And each of these points, I will denote them by the lowercase omega. Okay? So this is just a set of objects. Okay? Then we'll make, starting from the sample space, we'll build a probability space, which we'll define as a sample space, so this potato, okay, to which we equipped with a probability function, okay, which will be a function p which assigns numbers, probability values, so numbers that we call probability values, to each element or subset of omega. Okay? So to that, we'll add a function p, which will be able to evaluate on, for example, individual sample points. But also on subsets, any of them. And since omega is a subset, I mean, since if I say that I can evaluate this function p on any subset, that also includes omega itself. Okay, and so I will also be able to evaluate this. Okay, so a probability space is a sample space together with these functions, with this probability assignment function p. Okay, which takes as input a subset of elements from omega and returns. So P is defined as a subset from omega. Okay, so this calligraphic P represents the set of all subsets of omega. So it takes a subset as input and produces a number. Okay. then we have three axioms. The first axiom is that for any element omega in the universe, we must have that P of omega is greater or equal to 0. That's the first axiom. Then the second axiom says that the probability of the universe itself, so P of big omega, is equal to 1. And finally, the third axiom says that the probability that we assign to a subset of n elements from omega correspond to the sum of the individual probability values of the elements in the subset. Okay? That's it. We have defined what we mean by a probability value. You take any function p for which this is true, and you can call these numbers probability values, whatever they represent. Okay? We've never talked about the frequency of an event or something like this. The only thing we need to properly define a probability values is to define this sample space together with this assignment function p. If it agrees with these axioms, you can call these numbers probability values. Bonjour. Questions? Okay, one thing which is also important for us when we talk about AI is that actually we can prove mathematically that if we want to use the probabilistic framework or to represent beliefs of an agent, so for example, how much we think or believe that the ghost is at this position, okay, then you can prove mathematically using the Finity's theorem that if you want your agent to be rational, then you must encode your beliefs using probability values that agree with this axiom for probability. Okay? So another way to say that, if you want to deal, if you care about rational beliefs, you must encode them using these probability values that follow the Kolmogorov axioms. Okay? If you don't do that, if you encode your beliefs using numbers that do not agree with these axioms, then you can show that there will be cases where your beliefs are inconsistent and can be used against you. Therefore, you are not rational. Okay? There will be contradictions in your beliefs that someone else could exploit. Okay? So even though this looks like just three simple definitions, they have profound consequences, okay? Also for us, directly for AI, because we'll use this framework to represent beliefs that we have about these hidden variables that we cannot see. Okay? All right, so let's take a very simple example first. Let's say we have a die with 6 possible rolls from 1 to 6. Okay? So in this case, we could represent this universe, each of the 6 possible outcomes using a set omega made of 6 elements, one for each of the 6 possible outcomes. Okay? So meaning the lowercase omega, I, would be, in this case, our sample points, each corresponding to an outcome of the die, as I said. And so that defines these two things together. They define the sample space. Then we define the probability assignment function P. Okay? And for example, we could assume that we have a fair die. Okay? And we could encode these beliefs as numerical values such that P of 1 equals P of 2 equals P of 3, 4, 5, and 6. And would be equal themselves to 1 over 6. Okay? And this 1 over 6, if you just write this, P1 equals P2 together with the assumptions that we have made for omega, together with the 3 axioms, then these things imply that necessarily P of omega for any omega in the universe will be equal to 1/6. Okay, it's a consequence in this case of the axioms and of these constraints that we put on each possible outcome. Okay? Okay, next we can define the concept of a random variable. So a random variable technically will be a function x, which is a mapping between omega and some domain. Okay, so from the sample space to some domain that define some outcomes. So for example, on this problem with the die, we could say that we define a variable which we call odd, okay, which could take 2 values, true or false, okay, and which we would define such that odd takes as input omega, so an element of the universe, and is defined, for example, as the rest of the division by 2 of the outcome. Okay. What is important to understand is that the probability assignment P induces what we call a probability distribution for any random variable x. Okay? So you define your probability space by defining omega and P. Then you define a random variable by just defining a function. Then a consequence of that, a consequence of P, is that it will also lead directly to a probability distribution for that random variable x. Okay? And we'll say that the probability, for example, that the random variable x takes some value xi, in this case, will be simply equal to the sum of the probability values of the elements omega in the universe, such that we only take the omegas for which the value of the random variable, when it's evaluated at omega, is equal to xi. Okay? And so, for example, the probability of the random variable odd, okay, if we just follow this definition, to take the value true, is equal to the sum over all the elements omega for which the odd random variable takes the value true. So in this case, 1, 3, and 5. And then we sum the individual probability values of these associated to these elements. So we'd have 1/6 plus 1/6 plus 1/6 equals 1/2. Okay? But what you should understand is that we don't define the probability values of the random variable. Okay? They are defined directly. They are a consequence of the probability space and of the function. Okay? And finally, we'll define an event E, which has a set of outcomes, so one or several values associated to a random variable. So for example, if we say that we consider n random variables jointly, then we'll define E as a set of possible joint outcomes of these random variables. Okay? And then we'll similarly say that the probability value that we associate to an event, okay, E is the sum over all the outcomes in E of the joint probability values of these random variables, taking the corresponding values. Okay, important thing about the notations. So I will define always or denote always random variables with uppercase letters. And usually we'll start with X and then follow the alphabet. I will usually denote realizations. So values that these random variables can take using lowercase letters, realizations. And usually I will use the same letter but in lowercase than the one used to denote the variable. So for example, if I want to denote realizations associated to x, I will denote them by lowercase x, but I may have several of them, several possible realizations, which I will index from 1 to 1. Then I will write the probability value associated to one realization as P, uppercase P, of x, the random variable x, taking some value lowercase x. Okay? And because I will use this convention that I will always write down lowercase letters, I will always write in lowercase letters the realizations associated to a random variable uppercase x. Sometimes I will just simplify this as P of lowercase x. Okay? Then the probability distribution, and that's important. The probability distribution of a random variable x, I will denote in the slides using the bold letter P, and on the blackboard using P with the underline. Okay? And here I'm talking about the probability distribution, not about the probability value. Okay? So the distribution in this case, for example, for a discrete variable, would correspond to a table that describes for each realization of x the probability value associated to each of these possible realizations. Okay? While if you write this is a number. This is not a table. Questions so far? Okay, so let's start easy. So now we are ready to properly define and play with probability distributions. So we'll assume today that we are dealing with discrete variables. So the variables, for example, x, is associated to a domain dx, which counts a finite and discrete numbers of values. Okay? So for discrete variables, the probability distribution can be encoded by a discrete list of the probability values of the outcome, so each of the realizations. And we call this discrete list the probability mass function of the distribution. Okay? So for example, a scenario that I will use today is this one, where we are reasoning about the weather. So we are reasoning about a variable w for the weather. We would simplify the setting by assuming that weather can only take 4 values. So the domain of the weather is made of 4 elements. It's either sunny, it's raining, it's foggy, or today there are meteors hitting the planet. Okay? So these are the elements in my potato omega. And then I make this sample space a probability space by also defining these probability assignments to each of the possible outcomes, okay, which at the level of the random variable w would correspond to, say, the variable w takes the value sun with a probability of 0.6, takes the value rain with a probability of 0.1, takes the value fog with 0.3 probability, and there is no chance that there will be an emitter. Okay? So this table, okay, is a representation of a probability distribution associated to a discrete variable. Okay? In this table, we call that the probability mass function. Okay, we can extend these distributions to more than one variables. Okay? And in this case, we'll be talking about joint distributions. And we'll say that a joint probability distribution, now over not one random variable, but over a set of n random variables, well, this probability distribution will specify the probability of each outcome of these random variables, okay, each joint and combined outcome of these variables. So, for example, here, it's still the same scenario with the weather, but we add another variable, a second variable t, which let's say corresponds to the temperature. Okay, and to simplify things, we just say temperature can be either hot or cold. Okay? Then we can define the joint distribution of these two random variables, okay, in this way, and we'll say, so what we'll have to do is to define the probability value of each possible configurations of these two variables, or each possible configurations of these n random variables in the general case. Okay? And this follows directly from our definitions. We say that the joint probability value of this joint outcome corresponds to the sum of the probability values associated to the omegas, for which, when you evaluate the random variables from 1 to n on this omega, we retrieve the same outcome, we retrieve the same realization, lowercase xi, x2 to lowercase x. Okay? Okay, next, and then we'll take a break. From a joint probability distribution, we can define, or we can derive other distributions. One of them is the marginal distribution. So a marginal distribution will be the joint distribution associated to a subset of random variables starting from a joint distribution. Okay? So the marginal distribution of a subset of collection of random variables will be the joint probability distribution of the variables contained in that subset. So if we start, for example, from the joint probability distribution of the temperature and the weather, which we described by this probability mass function with this table, okay, we can obtain, for example, there are two marginal distributions we could define. The marginal distribution of the temperature variable alone, or the marginal distribution of the weather variable alone. Okay? And this distribution is a consequence of how we have built the joint distribution in the first place. Or can be viewed like that at least. And so, for example, we would have that. So what we need to do is to marginalize out all the variables that are not in the subset that we consider. So if we want to reason about the marginal distribution of the temperature variable, we need to remove the other variable, the weather variable. This is what we call marginalizing out this variable. Okay? And we would do so by simply saying that now the probability value, the marginal probability value associated to each possible outcome of t correspond to the sum of the joint probability values, so as defined there in the previous tables, for where we just aggregate over all possible values of the other variables that we remove. Okay? So if we remove w, then the marginal probability of t corresponds to the sum of the joint probability value of t for any other value of w. Okay? And so very practically, that means you can just, for each row of the marginal distribution, so each row will be built by just summing the rows in the joint probability distribution by selecting the realization that we care about and then summing over the other variables. So in this case, we would select all the rows for which the realization of t matches, for example, with hot. Okay, that would be these two rows. And then we just sum all of them together. Okay, this is what this sum says. And the corresponding probability value, the marginal probability value of t, then would be 0.4 plus 0.1, okay, 0.5. Okay? And similarly for the other variables, except that here we would have to marginalize out the other variable, the temperature variable, instead of the weather variable. Okay? And so, for example, for sun, would need to select all the rows that matches with the sun value. So it's the first and the third. And then we sum all of them together because we are marginalizing out the temperature variable. So we need to sum the probability values of 0.4 together with 0.2, giving us 0.6 as a marginal probability value for the sun. Okay? All right, let's take a break. We'll resume in 10 minutes at 9:40. Okay, so to quickly recap what we've been talking about today, I've been talking about probability theories, and the reason we are doing that is that we want to encode our subjective beliefs about some environment. Okay, if you want to be rational, I can prove you that the only way to be rational is to encode, the beliefs that we have as probability values, meaning they must follow Kolmogorov axioms, which are there on the slides, which basically define what a number must be in order to be a proper probability value. Okay, however you interpret these numbers, this is not important. So we'll use this framework in our case to encode subjective beliefs. Then I've introduced the concept of a random variable, which is a function. First we define a sample space, a set of realizations of the world, together with a probability assignment function, which basically gives a number to each of these sample points. If you do that, then you obtain a probability space, okay, from which then we can define random variables by adding on top of that the definition of a function, which is a mapping between an element of the set omega to some domain, okay, and that function is called a random variable, even though the function itself, by the way, is deterministic. It's a function. Then this function together with the probability space as a probability distribution, okay, which we define as, so we define the probability of a realization, so one of the possible values that the random variable can take, as the sum of the probability values of the element in our potato, such that the evaluation function, the random variable function, evaluates to the corresponding value that we want it to have. Okay? From this, we define probability distributions, and we were talking about probability distribution over discrete variables, which we can encode at the end of the day by just a list or a table where we have as many rows as we have possible outcomes, possible values that the variable can take, together with the probability value that we assign for each of these outcomes. Okay? You can do so for one, but also for several random variables from 1 to n. In this case, the probability distribution would describe the joint probability value of each combined outcomes of the variables that you consider. Okay? From this joint distribution, you can say that you want to reduce the number of variables, so you want to remove some of these variables. That leads us to the concept of a marginal distribution, which is the distribution of a subset of a collection of random variables, and which we define as the joint probability distribution of the variables contained in that subset. Okay? So the marginal, in the general case, is also a joint, okay, but on fewer variables than the joint over all the variables in the environment or in the setup that we consider. All right, so this we have defined. Next, we can also define the concept of a conditional probability distribution. And we say that the conditional probability of some realization A, so let's say we have two variables, A and B, okay, and we'll say that the conditional probability of lowercase a, of some realization A, given a realization lowercase b for the other variable, we will say that it is defined as the ratio of the probability of the joint realization of A and B together, okay, and the probability or more specifically, and the marginal probability of B. Okay? So by definition, we say that the conditional probability of A given B is equal to the ratio, so this ratio, of the joint probability value of the two realizations together over the marginal probability of B alone. Okay? And that makes sense. So if we take this is our potato, okay? And inside, let's assume that, so we define two random variables, A and B, okay? And so there will be a subset of the element in omega for which A is equal to this realization, okay? This is, for example, this potato. All right? Now, we are also saying that we want to condition this to the fact that B takes some particular value B. Okay? So we can reason about that as well. What will be the sample points for which the random variable B takes that particular realizations? That will be some other potato. Okay? And if we say that we care about the conditional probability value of A taking this value lowercase a, given that B has taken this value, okay, then we are basically restricting it's as if we are saying that now our universe omega is not this bigger potato, it's only the smaller potato for which B takes this value, okay, and among those, we'll evaluate how often, or we'll evaluate how many sample points takes the value A, okay, and that will be given by this area. Okay, this is P of A given B. That's a conditional probability. Okay, because there we have that both the random variable A takes that value A and B takes the value B. Okay, and we count what's the proportion of those when over all possible events for which B takes the value B. Okay? So an example of that, if we consider again our problem with the two variables temperature and weather, we could be asking ourselves, starting from this joint distribution over the two variables, what is the conditional distribution of the weather if the temperature is hot? How do you compute these numbers? So how do you go from this joint to this conditional, or to this second conditional? Anyone? Yeah.
For example, the probability that it's sunny knowing that it's hot, it's just like the probability like 0.4 divided by 0.5 because the probability that it's hot is 0.4.
Exactly. So we just have to follow the definition of the conditional probability value. Okay, so let's just do it slowly. So if I'm interested, for example, by P of W sun given hot, then I've told you that this is defined as the ratio of the joint over the marginal. Okay, of the joint over the marginal probability of the conditioning, so of the hot value. Okay, and now that becomes much easier. The joint probability value of this event, I can just read it directly from the joint probability distribution, the table. That's the first row, so 0.4, as you said. And now we have to also compute the marginal probability of hot. In this case, we just select all the rows for which the temperature takes the value hot. We sum all the probability values of all these rows. So in this case, that corresponds to the two first rows. So 0.4 plus 0.1, and that gives us 0.8. Okay, and you can do the same for all the other entries of the conditional probability distribution. Yeah, also maybe one thing now in terms of notations. So notice that I'm still using the letter bold P, okay, because I want to denote the distribution, so that table, okay. So P remains a table here, okay. If I add instead written P of W, some lowercase w, given t equal hot, this would be just one of the entries of that distribution. Okay, they are not the same. Is it clear for everyone in terms of notations? Okay, so now that we have defined all these concepts, joint probability distribution, marginal distribution, conditional distributions, we can define the generic problem that we'll be interested in, which we call inference. Okay, so I will define probabilistic inference as the problem of computing a desired probability or a probability distribution from other known probability values. So, for example, it would mean that we want to compute some marginal distribution of some conditional distribution or vice versa. Okay? So an example would be that, I don't know, if we are dealing with a setting where we are modeling the fact of whether or not you would arrive late today in class, okay, you could model that with a few variables. One of them would be a Boolean variable which would say that you arrive on time. Okay, you were there at 8:30. But of course, this probability value may change, or your beliefs may change when you start and you drive home, depending on what you know or don't know about what is on the road. Okay. So, for example, if there is no reported accident, then you may be very confident that you are on time for the class. Okay, and these numbers, 0.9, would be your confidence about that value being true. However, and this is why it will become interesting, these probability values will change depending on the evidence, depending on the observations that you have about the environment. So if you add another variable, like how early you wake up, or how early you leave home, let's say there is no reported incident and you leave home at 5 a.m., then that should increase your belief, you should become more confident, certainly, that you will arrive on time in this scenario. Okay? Because now we have conditioned to an extra evidence variable. Okay? If it's raining, on the other hand, if you take into account the weather, then it may lower your beliefs about the probability about arriving on time or not. Or if we go back to the ghost problem that we were trying to find on the grid cell, on the grid world, for example, your prior beliefs about the ghost being in cell 3.2 may be very low at the beginning when you have not observed anything. But if you observed a red value with your sensor at that precise location tree too, then suddenly you become much more confident about the actual position of the ghost. Okay? So the important concept is that observing variables, observing new evidence usually will make us update our beliefs about the things that we don't know. Okay? And typically the question we'll be trying to answer is, given that you observe this thing, what is the probability of H? And so mathematically, the object that we'll be trying to estimate over and over is the posterior distribution of the hidden variable H given one or several observations. Okay? And already you should recognize that maybe we can obtain this guy by starting from the joint of P and of the hidden variables and the evidence variable, and then we condition it on the evidence that we have. Okay? The issue which will happen is that maybe there is only a subset of variables that I'm really interested in. For example, the fact that I have on time, even though what I observe may depend on other factors. So I'm just trying to be consistent with the notations. Yeah. So maybe we have some other variables Q. And we want to query Q. We want to estimate Q given E without really caring about H. Okay? So in this case, what we'll be trying to estimate is the probability distribution of some variables of interest that I don't see directly, only indirectly, given some evidence. Okay? And we will try to do so regardless of the values that H can take. Because I don't really care about these variables. I put them inside my model because I believe they are important to properly describe the observations that I'm making, okay? But I'm not really interested in these variables when I want, for example, to make a decision, like trying to kill the ghost. That's the decision. All right, so mathematically, we'll assume that we have a set of evidence variables, E1, E2 to EK, that we do observe. So we have some specific value for each of them, okay? Or we have a joint realization of these evidence variables. We'll consider query variables, Q, that we don't observe, okay? If we were observing them, then we would be done. We have hidden variables, H1 to HR. All together, so when you join the E variables, the Q variable, and the hidden variables, they would correspond to the variables that we assume for the distribution that we consider, okay? So from x1 to xn. And I will properly now define what I mean by inference. Inference for me now will be the problem of trying to compute this posterior distribution of the query variable given some particular observations of the evidence variable. Okay? Let's take this example. How would you Okay. How would you retrieve the distribution of the variable W? How would you compute it, knowing this joint distribution to start with? Where in this case we would have three variables: the season, summer or winter, the temperature, hot or cold, and the weather, which is sunny or rain. Yeah.
And for each type, we will do the sum of the probability.
Okay. So, what would be each value?
Sun 0.65 and rain 0.35.
Okay, so this would be a table. We would have W and the probability. You said it could be either sunny or rainy. And how do you compute these values?
For all the sun, we do the sum of the probability.
And so what would you obtain?
0.65.
And for the rain?
0.30. Yes, 0.35.
35. I'm not checking if this is correct. It looks correct because it should sum to 1. But please check that this is correct. Okay, so that is it as just a marginal distribution, as if, so this would be the case where Q is W. There is no evidence variable. So E is an empty set of variables. And the hidden variables are all the other variables, in this case, the season and the temperature. Okay? What about this one? The conditional distribution of the weather given that we are in winter. So again, it's a table where we would have to iterate over all possible values of the weather. So sun and rain. How do you compute that? Yeah.
And the same as before, just we divide by probability of the result.
What do you, can you
So
be-
we call that in the result, so sun there 0.1, sun is 0.15, that it's 0.25, and we divide by the probability of the winter, so we need to add 0.1, 0.005, and so on.
So what would be this number? 0.5? How do you obtain that? What's the calculation you are doing?
For the marginal distribution of
Okay, so let's maybe rewind. So we have, for example, that P of sun given winter by definition of the conditional probability is the ratio of the joint of the two over the marginal probability of what is after this bar. Okay. Now, this is a marginal distribution. This is also a marginal distribution. It's a marginal distribution where we have marginalized out the season variable, while here it's another marginal distribution but for which we have marginalized out two variables, the season and the temperature. Okay? So, P of sun and winter. P of sun and winter. So it would be the 5th and the 7th row. So it's 1 plus okay, where we just sum over the possible, we iterate over all possible values that the other variable that we marginalize out can take. So in this case, we are removing the temperature. So we iterate over either hot and cold when winter and sun are fixed. Okay, so in this case, 0.1 and plus 0.15. And here we should be doing the same. The marginal now probability of the winter. So we just select all the rows for which there is winter, and then we consider all possible configurations of the two other variables. And so in this case, we would have to sum over all these 4 rows. Which is equal to, so 0.25, 3, 5. Okay, and you are correct. Okay, for everyone? So this can be properly defined by an algorithm which is called inference by enumeration, in which we would start from a joint probability distribution over all the variables. So Q, the query, the evidence variables, and the hidden variables. Okay? And let's say we want to compute the conditional distribution of the query given the evidence, marginalizing out the hidden variables. How do we do so? We select all the entries that are consistent with the evidence. So that's what we did there. For example, here, we selected the entries consistent with the evidence, so all the winter entries. Then we marginalize out the hidden variables to obtain the joint of the query and the evidence variables. So in this case, the joint of the query and evidence variables, which you obtain by just summing the rows by considering all possible configurations of the other variables, in this case, the hidden variables H. Okay, so that gives us access to the joint of PQ and the evidence. Okay, and then finally we normalize. We compute the ratio of the joint over the marginal. Okay, that's the joint over the marginal. And the marginal, we have to also compute it. We can obtain it from step 2 by marginalizing out now the query variable. That would give us the evidence of the realization. So that would give us P of, so the probability of the observation, the marginal probability of the observation. Okay? So this works, but to be honest, this is very inefficient. So if you think about the complexity of this algorithm, let's say we have n variables, and they can take at most d values, each of them. It means basically that we need to instantiate this table. How many rows does it have? Well, d to the n, because we simply have to enumerate all possible combinations of the variables, or rather of the values that the variables can take. So it's d to the n, it's exponential in the number of variables. And the time complexity is also proportional to the size of this table, so it suffers from the same exponential complexity in the number of variables. Now the question I will ask you is, can we maybe try to reduce the size of this representation? Can we reduce the size of this table such that maybe we could iterate over fewer rows? Okay? In which case, running this inference algorithm would be faster. And the answer is yes. Using two, you can do so by making additional assumptions. Okay, but we'll go there step by step. The first thing that we can define is the product rule, which says that the joint probability of some event made of two variables taking values A and B can be factorized in several ways, but one way is by factorizing it as the marginal probability of B times the conditional probability of A given B. Okay, that's the same as the joint probability of A and B. Okay, we are just saying the joint probability of having A and B is just the same as the marginal probability of B first, and then multiplied by the conditional probability of observing also A when I've observed B already. Okay, this is just saying that. And so that means we can use this rule to take maybe a big joint distribution and factorize it into smaller factors. Okay, like for this one, this joint probability distribution over the two variables can be written, re-expressed in terms of these two conditional probability, in terms of first the marginal distribution over the first variable W times a conditional distribution of D given W. In this case, it does not help. We have more rows than before, but we'll see that if we are making then a few assumptions, we'll be able to reduce the number of rows in these factorizations. Okay. The chain rule, the product rule can be extended and generalized to more than two variables, and that gives rise to the chain rule, which says that if you have n variables, then you can always factorize it. You can factorize the probability distribution of the joint outcome as the product of conditional distributions, and actually marginal conditional distributions of these variables conditionally on others. And the way you can do that is by increasingly adding the variables to the conditioning part of the conditional distribution. So if we take this example first with three variables, the joint distribution of x1, x2, and x3 can be just expressed as, or the probability of this joint event can be expressed as the probability of observing some value x1 for the first variable, okay, times the probability of then observing x2 for the second variable when I am in the scenario where I've already observed x1. So this is what you encode by the conditional probability of x2 given x1. And finally, times the conditional probability of x3 given both x1 and x2. Okay, and you can generalize that to n variables by just having a product over the n variables that you consider. And what you have to do is to multiply together the conditional probability values of xi given the values of the other variables that precedes xi in some ordering that you pick. Okay? So that will give us a way to factorize a distribution, okay, in terms of smaller factors. Okay, but how do we reduce the size of these factors? Well, we will need to make assumptions, and assumptions that we can make are assumptions about the independence of the variables, the statistical independence of the variables. And so we'll say that two variables A and B are independent if and only if for all values of A and B, we have that the conditional distribution of A given B is the same as the marginal, the conditional probability of A given B is the same as the marginal probability of A. If you have that, then that means A and B are independent. And similarly, you will also have independence if for all pairs A and B, the conditional probability of B given A is equal also to the marginal probability of B. Okay? Another way to say the same thing is to say that for any pair of A and B, the joint probability of these two values, P of A and B together, is equal to the product of the marginal probabilities of these two values. Okay? When that happens, you have independence between A and B, which will denote using this symbol. So they are perpendicular, they are independent. Okay? Okay, the setting they choose to describe in the textbook is a bit peculiar, but this is the one they choose. So they assume a scenario where you are at the dentist, okay, to make everyone comfortable, and you describe the setting in terms of 4 variables. So you go to the dentist because maybe you have a cavity, okay, and you are in pain. So these are 2 variables that describe yourself. Then the dentist comes and uses its instrument, its probe, to go over the teeth. And it will either catch or not the cavity if there is one. Okay, so the catch variable will be correspond to this Boolean outcome of whether or not you catch the cavity. You also decide to put the weather variable to describe the setting. Okay. Obviously, you can make assumptions about how some of these variables relate to one another, and the fact that you're in pain or the fact that the dentist managed to catch the cavity has nothing to do with the weather. That's a reasonable assumption that you can make. And so specifically, you can assume that weather is independent to all the 3 other variables. Okay? Which means that now you can rewrite a joint distribution over the 4 variables to take catch, cavity, and weather by assuming independence as a product of a joint over the 3 first variables times the marginal distribution over the weather variable only. Okay? So if you assume 4 different values for weather, and we assume that to take cavity and catch are Boolean variables, they can take 2 values. Okay? Initially, this joint would be described by a table of 32 entries. We just enumerate all possible combinations. So 2 times 2 times 2 times 4, that's 32. Okay? If we factorize it in this way by making this independence assumption, then what we would obtain is a joint which we can describe by 2 times 2 times 2 rows, 8 of them, plus 4 rows. So that's 12. So in this way, we reduce the size from 32 rows to 12. Another example would be if you take a coin and you flip it n times, you would have you can describe this scenario by having as many random variables as you have outcomes. So if you flip it, 10 times, you would have 10 possible outcomes. Each of them would be associated to a random variable, the first outcome, the second outcome, the third, and so on until the 10th. So you can describe the joint distribution of these outcomes using a big table where you enumerate the values that these 10 variables can take together. In this case, you would have 2 to the 10 rows, so 1,000 rows in your table. That's a bit silly because you can certainly make assumptions about the independence of 2 rows, of two coin flips. And if you make these assumptions, then in this case, the conditional distribution of these n coin flips could be rewritten as the product of marginal probability values of the individual coin flips. Okay? And in this case, we would have something which is proportional to 2 to n to instantiate this table. Here we only need to describe each of the n marginal probability distribution. Okay, so we'd have n times how many rows we have per marginal distribution. We have 2. So in this case, that would be now linear with the number of variables instead of being exponential in the number of variables. Questions on this? All right. We can make other kinds of assumptions that are still related to independence, but not as strong. And the assumptions that we can make are called conditional independence. So we can say that 2 variables are independent, not always, but only conditionally on some other variable. Okay? And so we would say that A and B are conditionally independent given a third variable C if for all pairs of values of A and B together with, no, sorry, if for all values of A, B, and C, we have that the conditional distribution, the conditional probability value of the first variable A given B and C is equal to the conditional probability value of A given C without caring about B. Okay? Or similarly, we would say that they are conditionally independent given C when the conditional probability value of B given A and C is equal to the marginal, to the conditional of B given C. Okay? Or another way to say that is if the joint distribution of A and B given C can be written as a product of marginal conditional probability values, in this case P of A given C times P of B given C. Okay? In this case, we would denote that in this way. So we would say that A and B are conditionally independent given a third variable C. Okay, so why is this useful? Because if we use the chain rule, which we can always use whatever the distribution, okay, we can start from a joint distribution and factorize it in terms of the conditional given some other variables. Okay, so using the chain rule, we can factorize the joint as a product of conditional distribution. And then if we make conditional independence assumptions, then that means some of these terms, some of the factors that appear in the product may be simplified because of the independence assumptions that we are making. Okay? And that's precisely what we can use to scale up the probabilistic model to a large number of variables by making these assumptions. So as an example, let's now assume that we restrict ourselves to the 3 variables at the dentist without talking anymore about the weather, so toothache, catch, and cavity. We can define this with a joint distribution over the 3 variables. That would be a table which would correspond to, which would have 8 rows, 8 entries. Okay? But using the chain rule, this can be written as first the marginal probability of the cavity times the marginal probability of catch given the cavity times the conditional probability of toothache given catch and cavity. Okay? This is always true. However, now conditionally on the fact that you assume that there is a cavity, then one thing that you can reason about, or for which you can make a reasonable assumption, is that the toothache and the catch variable can be said to be independent given the cavity. Okay, what an assumption you could make is that what defines whether or not you are in pain or not only depends on the cavity. It does not depend on the fact that the dentist catches the cavity or not. Or vice versa, the fact that the dentist catches the cavity should not depend on whether or not you are in pain, conditionally on the cavity. Okay? So that's an assumption that you can encode using a conditional independence assumption, which would, in this case, allow us to rewrite this conditional given the 2 other variables as a conditional of the pain variable given the cavity and only that. Okay? And this is nice because that means now we need even fewer rows to represent this distribution. Okay? And so in this case, we can show that the representation of the joint distribution will reduce to 2 plus 2 plus 1 independent numbers, so numerical values that we would need minimally to represent the distribution. Okay, instead of the case where we would instantiate the whole table, in which case we would need 2 to the n minus 1 numbers. Okay, another example of that is the naive Bayes model, which is a very simple model but quite useful and very often effective. So let's take the. So let's assume that I don't know. We are in a medical setup, and we are trying to study or to model a setting in which we would have causes and effects. So, for example, the cause could be that you have some disease, and the effect would be symptoms that you observe. Okay? Now, given observation of the symptoms, you want to query the cause variable. You want to know, to determine the posterior distribution of some disease given some symptoms. Okay? That's exactly one of those scenarios. Okay? So we could describe the whole system as a joint distribution in which we have the cause variable and a series of, let's say, n effects, each of them encoded by its own random variable. And then using the product rule, we can always factorize this joint as the product of the marginal probability of the cause times the joint and conditional probability of the effects given the cause. Right? So with that, we don't gain anything. But if we make pairwise conditional independence, saying that two effects are independent given the cause, okay, what really matters is the cause, not. It's not because you. I know. I will not find a good example like this, but yeah. How do you call that? So if you have a disease like the pox, like varicella, okay, you may have temperature and skin lesions. Okay, these are two symptoms. But you can also assume that the symptoms are conditionally independent, given that you know that you have the pox or not. Okay, it's not because you have temperature that it's more likely that you will have also skin lesions. Okay, if you don't condition that on the cause. Okay, so in many scenarios, you can make these fairly reasonable assumptions, saying that the effects are conditionally independent pairwise given the cause, given some other variable, and in which case this joint distribution, this conditional and joint distribution, can be rewritten itself as a big product, but now where we have n factors, but each of them is very small because it's a tiny marginal distribution of one effect only given the cause. Okay? And basically, this makes inference under this model linear instead of being exponential, so that's very inefficient and often very effective. Okay, next we arrive to the main slide of the course, and I'm saying the course, not the lecture, the course. So we arrive to the Bayes rule. So the Bayes rule, we can derive it from the product rule that we apply in the two directions. So I've said that the product rule says that the joint distribution of two events A and B, or a joint event A and B, can be rewritten as the marginal probability of A given B times, the conditional probability of A given B times the marginal probability of B. But we can swap A and B. The product rule will remain true. Okay, so that means it can also be written as the condition of B given A times the marginal of B. Okay, now if you okay, so we have P, A, and B equal to P of A given B times P of B. Equals to P of B given A times PA. Okay? Now, if we forget about this, we can rewrite this by just dividing both sides by P of B, right? And that would give us P, the condition of A given B, which we can re-express as P of B given A times PA over the marginal probability of B. Okay? So this thing is known as the Bayes rule. In which, in our setting, we'll say that PA, for example, will correspond to what we call a prior that we have on A. So it's a marginal distribution which, let's say, encode our prior beliefs about the value that A can take. Then we have this term, which is the likelihood, which defines the probability of observing B given A. Okay? And these two of them together are proportional to this conditional distribution, which we can interpret as a posterior distribution that you obtain by starting from our beliefs about A and then observing B. So we will say that we start from some belief and then we update these beliefs using some observation B. Okay? And this update can be mathematically defined by this equation. Okay? The Bayes rule. So this is the mechanism we'll use over and over for an agent to update its belief when it receives observations. It will maintain some beliefs about everything it cares about, but does not see. Okay? It will only see evidences, like this, but it will be able to update its prior beliefs using this rule. Okay? And then if it gets another observation, it just reuses the prior, the previous posterior, and iterate like this. Okay, another way to say that, let's say we consider this scenario in which we observe that the ground is wet. Okay, and then you are asking yourself, did it rain during the night? How do you solve this question? Well, you can start by some prior beliefs that you may have about the fact that the ground is wet. It could be wet for several reasons, because it rained, or because you poured some water on the ground, or whatever other reason. Okay? That's your prior beliefs that you have. No, that's an observation. So, no, sorry, you may have, sorry, no, what I said is wrong. So you want to reason about the weather, in this case, whether or not it rained. Okay? But you don't observe that because you were sleeping. So you may have some prior beliefs about how likely it is that it's raining in Belgium. Let's say 0.9. Okay? If you are living somewhere else, it could be lower. Then you wake up and you observe that the ground is wet. What happened? Can you use then this observation, the fact that the ground is wet, to update your beliefs about the weather that happened during the time that you were sleeping? Okay? And you can do so by just starting with your prior beliefs, 0.9 or 0.5, I don't know. And then you have the likelihood, which is to say that if you assume that it rained, how likely is it to observe that the ground is wet? That's something that for which you can have a model. That's precisely this model. Okay, that's something that you encode with a conditional distribution about what is the probability of some evidence the ground is wet, given that it rained. Okay? And so by doing so, the mechanism that we'll use is that we may have some prior beliefs about all possible scenarios. Okay, that's what we encode with this distribution. And then we will only keep those that are compatible with the observation B. Okay? And we'll basically reweight, we'll increase the probability of all those events that are compatible with the observation B, and vice versa, all the configurations of A for which the observation B is very unlikely, their probability will decrease. Okay? And this mechanism is encoded by this very simple equation. Okay? You just reweight your prior beliefs by the probability of the event, the observation given some cause or given that variable A. Okay, does that make sense? All right, as an example, what time is it? Yeah. Let's go back to our problem in which we would like to determine the cause given an effect. You observed that you have temperature. How confident can you be about the cause, about whether or not you have some disease? So the example I will use is the case of the cause would be a disease, the meningitis, and the symptom S would be whether or not you have a stiff neck, so you have a courbature in French on the neck. Okay? Now you have a stiff neck. Are you ill? Should you go to the hospital? So you can model this scenario by saying that you have some prior beliefs, marginal beliefs about how likely it is for anyone to have meningitis. Let's say 1 over 50,000 chance. Okay, that's your prior beliefs. But then you do observe that for your patient or for yourself, there is a stiff neck. Okay, and you say that you also assume the knowledge that if you do have meningitis, then the probability of a stiff neck is 70%. Okay, so if you are ill, you will have with 70% a stiff neck. Okay, now you do have a stiff neck. What's the probability of the meningitis? That's the question we want to answer. Given the effect, what is the probability of the cause? So given the effect, what's the probability of the cause? Unfortunately, we don't have this diagnostic direction going from effect back to the cause. We have the opposite direction going from the effect, from the cause to the effect. Okay, that's what we encode here by this knowledge. Okay, but that's fine because we can reverse, we can swap the two variables using Bayes' rule. Okay, we know by the Bayes' rule that the posterior probability of the disease, the meningitis, given a stiff neck, can be rewritten, or it's just proportional to our prior beliefs about the meningitis multiplied by the probability of a stiff neck given the disease. Okay? We have also the marginal probability of the stiff neck, which appears at the denominator. So then you replace all these elements by their values, and we would find that the probability of having meningitis, if you have a stiff neck, in this case, remains low, and the value would be 0.0040. Okay? What I will show you now is how to solve the Ghostbuster problem, the one that we started with today, using this very same mechanism, using the Bayes rule. And so how can we do that? How can we solve the game using the Bayes rule? So we'll assume that we have a random variable G for the ghost location, okay? And a set of random variables, one for each of the cells, which will correspond to the readings that we obtain with our sensor, okay? And let's say we don't observe anything yet. We start from a prior beliefs, which is uniform, which says that I don't know, and I will just assume that the ghost can be anywhere on the grid, and I don't have any preference about this position. Okay? So I will have a uniform prior distribution over the ghost locations. Okay? So for example, if you have 5 by 5 grid with 25 possible positions, and so the prior probability value that we'll assume for the ghost position would be, in this case, 1 over 25. Okay? We assume that we know our instrument. We have an observational model, so we know how the evidence variable relate to the variable to the hidden variable. So in this case, the evidence would be the readings, and the hidden variables would be, and the query in this case also would be the ghost location. Okay? So we assume that we have this knowledge. Okay? We have a probabilistic model of the instrument. So to give you an example, it could be, for example, that Rij would correspond to the color that you read at some cell Ij. And we would simply say that when I say that I know this model, it would be the same as saying for every possible value of G, okay, and any value of the variables, of the reading variables, I have defined these probabilistic assertions which correspond to the beliefs that I have. For example, that if the ghost is at position 1, 1, then the reading for 1, 1 would be yellow with a probability of 10%. Okay? We also make the assumption that two readings are conditionally independent given the ghost position. Okay, so how do we use then the Bayes rule to update our prior beliefs given this setup? Well, what we want to obtain at the end of the day is the posterior distribution of the ghost given all the readings that we have done. Okay, so mathematically, we want to estimate the conditional distribution of the ghost position given the readings. Okay, and by the Bayes rule, this can be written as the ratio of our prior beliefs about the ghost position, but updated by how likely is the reading that we obtain given the ghost position. And that's what we know as well, because we assume this observational model going from the ghost to the readings. Okay, we have assumed this element. Okay, and then how do we use this then iteratively? Well, we can start from an empty grid with some prior beliefs. We collect one observation. We sense one of the cells. We use the Bayes rule then to make an update, meaning that now we'll have updated beliefs about the ghost positions given that first reading. And so now the beliefs will no longer be 1/25, but will be other values. And then at the next trial, when I want to obtain a second reading, I can integrate, I can update my current beliefs by starting from the posterior that I obtained after the first step. I will say that that posterior becomes my prior beliefs. And again, I use the Bayes rule to update this prior, but now using the second observation. And you can do so repeatedly to obtain the posterior distribution over as many readings as you want. Okay, so in this video, this is what you will see. We start from a prior beliefs uniform about the ghost position. Here, if you were to sum all these 0.02, you would notice that it's not equal to 1. It's not an issue of the engine, it's just an issue because these numbers are rounded before being displayed. But it's actually a uniform prior belief. Okay, so we make a green readings. So intuitively, when you have a green reading, you know that it becomes less likely that the ghost is there. That's what we do without even realizing that. But if we just compute the posterior probability values with the Bayes rule, this is exactly what you will obtain as well. You see that now these values at the green cell, but also in the neighborhood of the green cell, becomes lower than before. Before they were at 0.02, now they are smaller than 0.01. And also that the probability of the ghost being at locations at least 4 cells away has increased. Okay? So, for example, these cells now have a higher probability of having the ghost. The same for this one, and this one. Okay? Okay, eventually the video will make another observation. Okay? Yeah, by the way, that's what, yeah, I should have talked about that. If we are there and now you see these numbers, where would you hit next? Would you probe this cells in the neighborhood of this one. No. But when we were playing that game before, this is what we were doing. But that's very inefficient. Okay? It should be obvious that we should not probe these cells if you want to be also efficient. Okay? Where would you probe the next cells? Certainly the regions for which you are the most uncertain. Because you want to collect information and to reduce your uncertainty. That's what you want to do. So at one of these corners, it's probably a very good idea to collect an observation. Okay, if we collect an observation there in the top right corner, it's yellow. We use the Bayes rule again to update our beliefs. Now we get these updated beliefs, which correspond to the number that you see in the grid. Where would you hit next? Yeah, in one of these high probability cells. And then you see that after only 3 hits, the probability of one of those was already 97%. Okay, if we make a fourth observation next to it, then it becomes larger than 99%. So that game becomes very easy. Okay, we can make more observations if we want. That will just keep reducing the uncertainty. And eventually, when we are very confident, we can just try to kill the ghost. Okay, this is just the Bayes rule. Huh? This is just this equation.
But
yeah.
I don't understand how we take in account the distance between the observation and all the other.
But this is what you encode there in your observational model. So you will have one variable ij for each position. Okay. So this rij. So you will have many of them in the game there. I don't know how many there, but like 50 of them, let's say. And then you assume that you can determine the probability of having let's say the ghost is there. Okay. And you are asking about here, 1, 2. So here, that would be P of R ij given G equals something that you assume, okay, like this one, or 3, 4. So 1, 2, and 4. Sorry, 4, 1, 4, 3. Okay, and under these assumptions, okay, so you're asking if you assume that the ghost is there, what is the probability of having a yellow reading at position 1, 2? Okay, and there you can compute these distances and so on, and associate these distances to probability values, for example. Okay?
Okay, but how do we know the distance between the case 1, 2 and the case 4, 3 with only the Bayesian rule?
What do you mean?
Like the probability is depends on the distance of one case
Yeah.
and the case where we made the observation.
Mm-hmm.
So how do we take in account this distance on the Bayesian?
Well, because it's encoded in the likelihood function. The likelihood P of B given A is exactly what we are defining here. It's the probability of some reading taking some value given some position of the ghost. That's the likelihood term. Yeah.
But we have to know how noisy the sensor is.
Yes. Yeah, you need knowledge of your instrument. That's what we call an observational model. So you assume that you have a likelihood, it's known, it's given. It may not be correct, that's another issue, but you assume that you have something. Other questions on this? Okay, so this Bayes rule is really important. If it was not clear, it's really the foundations of many AI systems. So basically, every time you have to take a decision, the optimal thing to do is to be Bayesian. And to be Bayesian, you need to integrate, you need to account for uncertainties about things that you want to reason about, and you can do so using the Bayes rule. All right. One last example to also show you that this Bayes rule is not only useful to play Pac-Man. There are plenty of more interesting problems that you can solve with this. One of them is science. It's a very broad topic, but in many cases, in scientific studies, what you would have is a scientific simulator. So you are basically studying some physical process of some sort, for which you have some knowledge. And so you can assume that, or you have designed yourself a simulator that describes what you are currently studying. Okay? This simulator can be implemented or could correspond to just a conditional distribution of things, stuff that you observe, X, conditionally on some value of the parameters of this model. Okay? So you can say if the values of the parameters were 1, 2, and 10, if I run my simulations, then I expect to observe something. Okay? And these simulators can be very complicated. They can simulate physical process. They can model, I don't know, experiments around them, and so on and so forth. So you can put a lot of knowledge inside. But usually what will happen in science is that you are interested not in the observations themselves, but, for example, in trying to measure or estimate parameters of your model. Okay? And you can frame this as a Bayesian problem, as a Bayesian inference problem, in which you are trying to estimate the conditional distribution of parameters, input values that you should put inside your simulator to reproduce what you have observed. Okay? And using the Bayes rule, you can rewrite this as a ratio of some prior beliefs you may have about these model parameters times the likelihood of the data given model parameters, and P of X given theta is the scientific simulator itself, in this case, over the marginal probability of this observation. So to give you a concrete example, this is something that we are working on in my group, where one of my PhD students is studying exoplanets. So this is in collaboration with astronomers. And so astronomers have detected thousands of exoplanets now, and they are trying to understand if any of those is interesting, if it's Earth-like, for example, if it's habitable. And one way to try to assess that is by trying to understand the atmospheres of these planets and the chemical compositions of the atmospheres of these planets. For example, is there water? Are there CO2s? And so, things like this. We don't have clear pictures of these planets. Neither can we go on the planet and check for ourselves. They are so distant that certainly none of us will be able to go there anytime soon. But however, what we do observe are spectra, like these ones, which are basically the kind of data observations that you can collect from telescopes, like Earth-based telescope or telescope that you have in space. And so we get this kind of observation. That's an X. That's one of the observations. And just like for the Earth, we have scientific simulator of atmospheres of other planets. And so we can simulate, if we were assuming some value of the parameters that control the atmospheres, we can simulate the observation, the spectra that we would observe by some instrument. Okay? And all this knowledge would be inside the simulator. And so this can be done. We have forward simulator going from parameters to data. And then what we want is to inverse this process. We want to start from data and recover model parameters. Okay? And we can exactly frame this as a Bayesian inference problem. Unfortunately, none of the algorithms that we'll see together in this course you can use to solve this problem, but there are others on which we've been working on. And this is the kind of, for example, outcome you could obtain if you see this spectrum that you collect from some instrument, then you can reason about values of the model parameters that are compatible with that particular observation. Okay? And the model parameters in these cases have a physical meaning. I don't know, they correspond to the mass of the planet, the ratio of molecules, and so on and so forth. Okay? And what you see there is a representation of the posterior distribution of the parameters of the model. Okay? All right, so to summarize what we have seen today, we have uncertainty and we have to account for it. It can arise from several reasons, either because we are lazy. We know stuff, but we are just too lazy to put it inside there, so we just approximate everything by unknowns, or because we are simply ignorant. We know there are things we don't know, and we will incorporate these known unknowns as additional variables, which we'll never observe, but which we can take into account nonetheless. You will have to deal with probabilistic environment for any interesting problem, except maybe for the video games, deterministic environments, everything will be easy, but as soon as you consider something closer to reality, you will have to deal with these uncertainties. How do we deal with that? One way is to use the probabilistic framework to encode our knowledge as probability values. Okay? And importantly, we'll use probability values to represent beliefs, subjective knowledge that we may have. Okay? It may be wrong or correct. That's not important. I mean, it's important if you want to make good decisions, but it does not really matter for then the framework that we've seen. And very importantly, you can use the Bayes rule to update these beliefs based on observations you may have. Okay? Questions, comments? Okay, then we'll follow with the exercise session. Let's say we resume in 15 minutes at 11:15.